Welcome to this lecture on third law of thermodynamics. So we have already gone through the first two laws. The first law states that the energy of the universe is constant. The second law states that the entropy of the universe is always increasing and it tends to a maximum. Till now we have come across four important state variables and parameters to characterize a system, which are volume, temperature, pressure, and in the second law as an offshoot we got entropy, right? Now all the four are required to characterize a system. Among this, volume, temperature and pressure can be exactly defined, but the problem is with entropy. The entropy has, if you know the definition, it is given by delta S is equal to Q reversible by T. So which means you are finding out the delta S for the processes. Now why don't we know what exactly entropy for that system is? So here we'll try to do an absolute entropy calculations. That is where we get into the third law of thermodynamics in our attempt to find out the absolute entropy of a system. So let's start for an ideal gas. Now from combining that is first law, which is du is equal to dq minus p dv, and from second law we have dq by t is equal to ds, right? So now I want to combine both of this, and what we get is du is equal to tds minus p dv at constant temperature. Du for an ideal gas is 0, so this implies that this is going to be p dv by t. And for ideal gas, pv is equal to nRT, so ds t equal to nr t by t nr by v. So therefore your t by t will be nr by v, and then we have dv at constant temperature. P dv is equal to this is equal to 0. So now this, if you expand, it is going to be p dv minus, no sorry, plus v dp is equal to 0, and p dv is equal to minus v dp. And your ds t, if you make the substitution, it is going to be nr dp by p. Now for an arbitrary pressure, if we want to get the entropy at a certain pressure p, so how do I do? I just integrate between pressure for an arbitrary pressure from p naught to p. So you will get it as s at pressure and temperature, constant temperature T, minus S at pressure P naught, temperature T is equal to minus nr ln P by P naught, where P naught is some reference which we set at 1 bar. Okay, and therefore what I can write is S naught P should be and if you want to calculate the molar entropy, now to finish, what do we know? What do we need is, we still need this delta S. If we know this at 1 bar at any temperature, so we can calculate at any arbitrary pressure and temperature. So this thing is still needs calculation. So how do we calculate? So suppose consider the following sequence of processes. You will get a hang of how to calculate. Consider the for the substance A. Now A solid from 0 Kelvin and 1 bar, it is going to A solid till melting temperature and 1 bar, solid liquid Tm and from here it will become A liquid boiling 1 bar, so again back it is becoming A. Okay, so one is from, there is a temperature difference here from 0 Kelvin to Tm, and Tm to here what is happening is the phase transition is happening, that is fusion. Okay, and again there is a temperature is increasing, and again here what is happening is a phase transition. Okay, and again from here to here the temperature is increasing. Now what we want is, we want to calculate the entropy of this calculate the entropy here. This gas. Okay. So this can easily be calculated using this relationship. Okay. Just a minute, we'll come back to that. We'll derive two equations and then we'll come back to this. So du is equal to TdS minus TdV. So what is ds? ds is equal to du plus TdV. So by dt constant V dt at constant V. So this is same as Cv by T. Similarly, dH is equal to TdS plus V dP. What is ds here? ds, did we miss something here? Oh, I think we have missed. This should be divided by T. So ds is going to be okay. Now here to calculate the entropy of the gas, now since the pressure is constant, look here, it's 1 bar, it's 1 bar again, it's 1 bar again, it is 1 bar. So the pressure is constant. You want to find a relationship where entropy is varying with temperature. So find a relation where entropy is varying with temperature and pressure is constant. That is exactly what we will get here. Okay, so using this, how do I calculate the entropy at one bar? First, I need to find out the value of at 0 Kelvin. Okay, and from there, from 0 to, for that process, from 0 to melting temperature, so the entropy increase is given by integral by T plus, now delta S is equal to dq reversible by T, okay, or delta H is equal to delta H by T for transition, any phase transition, for a phase transition. Okay. So that is what is happening here. Okay, so this phase transition from Tm, from solid to liquid, is given, the entropy increase is given by this one. So next, again, what will happen from Tm to Tb, Cp of liquid to dt by temperature, and again delta H gas. Okay. Now if I have to graphically represent this, it's going to be where delta S is equal to Cp dt by T. Okay, so using that previous relationship, where does it work? It works under in these three graphs, and here it is. So this is the temperature curve, and this is solid melts, and its entropy increase is given by vaporization. No, fusion. And liquid boils, and its entropy increase is given by now again we are caught up with this. We don't know the value of this particular thing. What is the entropy of that substance at 0 Kelvin? So this is where we enter into the third law. We want to calculate this entropy at 0 Kelvin. So this is where we enter into the third law, and this was first expressed as Nernst heat theorem. So Nernst in 1905 postulated that as temperature tends to 0 Kelvin, delta S tends to 0 for all isothermal processes in condensed phase. This was later generalized by Max Planck, who in 1911 said that as temperature tends to 0 Kelvin, your entropy tends to 0 for every chemically homogeneous substance in perfect crystalline state. Okay. And this itself what we call as third law of thermodynamics. which states that the entropy of all, these are different statements, okay, the entropy of all perfect crystalline substance is 0 at temperature is equal to 0 Kelvin. Now, what is the justification for this? How do we know that entropy is 0 at temperature is 0 Kelvin? So this is where we need to get into statistical thermodynamics. So it was Boltzmann who proposed that there is a link between the spread of molecules over the available energy and the entropy. Okay, so which he expressed as entropy is equal to, here K is, so this is called Boltzmann formula for the entropy. And K is called Boltzmann's constant. And its value is 1.381 joules per Kelvin. And W is the number of microstates, or the number of possible in which molecules of a system can be distributed. Total energy. Okay, to give you a brief idea of what is a microstate, so let us say you need to fill 3p electrons. Okay, so how do you fill? It's not just one way of filling, there are at least 6 ways where you can fill 3 electrons in p orbitals. One is 1 1 1. So which one is, it's not which one is correct, we have taken this to be the correct way of filling the electron. There is a rule for it. But what are the possible ways? So you can either fill like this, or you can fill like this, like this, like this, or you can fill like this, or you can fill like this, or you can fill like this, or there are, you can fill like this, like this. So there are n number of ways. So these are called different micro states, different possibilities. Okay, now coming back to this formula and our third law of thermodynamics. In a pure crystal, at 0 Kelvin, the indistinguishable atoms are located in an exact position, exact pattern of lattice sites. Right, this is true. In a pure crystal at 0 Kelvin, there are all the atoms are located in their own lattice sites. They are not, there is no defect there. They are exactly in their position. Now, there is only one way of achieving this. So W becomes equal to 1. Since there is only one way of achieving this, there are, you cannot have multiple ways of having the same having those many atoms in the exact location. There can only be one way. So W becomes 1. Ln W is equal to ln 1 is equal to 0, and therefore your entropy, which is ln W, is 0. So entropy of a pure crystal at 0 Kelvin is 0. So this is your third law of thermodynamics.